Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 15 on the subject of computer organization and assembly language programming. The title of today's session is Instruction Set Architecture Part 2. Well, in the last session we started our discussion on ISA of a processor, which is actually the set of instructions, registers, memory space and other features visible to the assembly language programmer. In the last session I said that there are 6 dimensions of ISA, but over here I have merged the control flow instruction with the operations. So for this course we will say that generally there are 5 dimensions of ISA of every processor. The class of ISA, types and sizes of operands it support, the possible operations that the CPU can perform, memory addressing models and addressing modes, and finally encoding of all this information in the instruction. Today we will talk about these 5 dimensions one by one in a bit of detail, and this is the same old slide that we discussed in the previous lecture. And let us start with the different classes of ISA. I will discuss 4 classes in today's session: the stack based, accumulator based, register and register memory. Well, dear students, in case of a stack based machine, the operands are implicit at the top of the stack for all the ALU operations. In this diagram you can see this is the processor, this is the stack, the ALU, and this is the memory. The ALU gets both the operands from the top of the stack, and finally the ALU places the result back on the top of the stack. The maximum number of operands allowed is 1. Let us suppose that this is the high level language instruction: A is equal to B plus C multiplied by D minus E, and this is the assembly instructions for a stack based machine that implement this high level language code. For example, first of all, since the precedence of this plus operator is the maximum, so we'll push B and push C, that is both the operands on the top of the stack. Then we will call the add operation, which will get both the operands from the stack. The ALU will perform the add operation and will place the result back on the top of the stack. And similarly you can see there is a push operation on this operand D, and then we have called the mul, and then finally we have popped the final result from the top of the stack. Well, the attributes of a stack based machine are the instructions are short, compiler is easy to write, however the code is a bit inefficient. The example of machines that implement this stack based architecture are HP 3000, and today's Java virtual machine also is the implementation of this architecture. The other architecture is the accumulator based machine. In case of an accumulator based machine, one of the operand is implicit and that is placed inside the processor register, normally called the accumulator. So one operand comes from the accumulator and one operand comes from the memory to the ALU, and the result is again placed inside the accumulator. To implement this high level language instruction, this is the assembly code that is used by an accumulator based machine, and the attributes of such machine is it is simpler to design, it has short instructions, however there are many load and store instructions involved. The machines that use this single accumulator architecture are PDP-8, IBM 7090, and today it is used in most of the DSP processor, digital signal processing architectures. The third architecture is the register machine or the load store machine. in which case both the operands are the registers. These are the registers of the CPU. Both the operands come from the register to the ALU, and the ALU places the result back inside some of the registers. The maximum number of operands that are allowed in this architecture are 3, and this is the assembly instructions that implements this single high-level language code. For example, you can see that in the first instruction we have load an operand that is located inside the memory in register R1. We have loaded the second operand in register R2, and then we have used the add instruction which adds the contents of register R1 and R2 and place them in the register R3, and so on. The attributes of these load store machines are that they allow fast access to temporary values being in the CPU registers. There is a reduced traffic to the memory, and the instruction encoding is simple and fixed length. However, the limitations are that the instruction count is comparatively high and there are many load store instructions. Example architecture that follow this load store machine are PDP-11, Cray-1, MIPS, PowerPC and Spark. The fourth class of the ISA that I am going to discuss today is the register memory machine, in which there is no implicit operand. One of the operand the ALU is getting from the register, and the other operand the ALU is getting from the memory. And after computation of the result, the ALU places the result back inside the general purpose register. Similarly, this is the high-level language instruction, and this is the assembly that implement this high-level machine, high-level language code. The attributes of this register memory architecture are we have smaller number of instruction count. However, the instruction length varies. The clock per instruction also varies, and of course, it is a bit harder to implement pipelining in these architectures. The example machines that follow this register memory architecture are IBM 360, Motorola 68000 and VEX 8086. So after having a fair idea about the 4 different classes of ISA, let us now move on to the second dimension of an instruction set architecture, and that is the types and sizes of operands that are supported in a specific ISA of a processor. The main question is, how is the type of the operand designated? By the type of the operand, we normally encode it in the opcode using the load byte or load word, and the common operand types are character, which can be of 8 bits, half word of 16 bits, word of 32 bits, double words of 64 bits, and we can have the single precision as well as the double precision floating point values as well. Well, our discussion about the sizes of operands will remain incomplete if we will not talk about the registers inside the CPU. And we all know that the smallest amount of memory that actually resides inside the CPU are called registers. And every CPU typically contains a few easily accessed registers built from the fastest technology available. The number and functions are, of course, a central part of any machine language. Well, dear students, there are 2 most important registers that every architecture have, and these are the instruction pointer and instruction register. The instruction pointer is also normally called the program counter, and this register stores the address of the next instruction to be executed by the CPU. For example, if these are the contents of a program counter, so that means the next instruction which need to be executed is located inside the memory at address 9. Similarly, once the instruction is accessed from memory, it is loaded inside another register that is called the instruction register. And this is the register which contains this instruction, and that needs to be decoded later on so that it can be executed by the CPU. And there can be different parts of this instruction. For example, this part might mean the opcode, these two parts might mean the different registers on which the operands are located. I will talk about this distribution in the later part of today's session, inshallah. Well, other than the program counter and instruction pointer, there are many other registers as well that are used to store data and memory addresses. They are accessible to the assembly language programmers, and their number vary from architecture to architecture. First of all, there are various data registers which are used to store temporary data during any ongoing operations. Their contents can be accessed by the assembly programmer. For example, consider this instruction, add instruction, which add the contents of two registers R1 and R2, and after addition it places the result inside the first operand. Let's suppose this R1. For example, if before the execution of this instruction, the contents of register R1 is 12 and the contents of register R2 is 23, so afterwards the R1 register will contain the sum of both these two registers, which is 35, and the contents of R2 remains unchanged. Other than various data registers, there are address registers as well inside the CPU, and these registers are used to hold the address of the location to be accessed from memory. For example, consider this instruction, assembly instruction of any hypothetical architecture, which says stores at the rate A, R2. So this says store the contents of R2 at memory location pointed to by this A. Suppose if this A contains 1 to 6 and this R2 register contains 35, so I mean we need to place the contents of register R2, that is 35, to the memory location pointed to by this A register, that is 1 to 6. So this 35 will be stored in the memory at address 126 after this instruction is executed. Well, in our next lecture, when we will be designing the ISA of our hack computer, we will see what all registers are required for that particular hack computer architecture. So now we have a fair idea about different classes of ISA and the types and sizes of operands. Let us talk about the third dimension of ISA, and that is the different operations that the ISA is designed to support. Well, dear students, there is a long list of operations that an ISA can support, like the arithmetic and logical operations, the data transfer operations, control operations, system, floating point, string, graphics, and so on. But most computers generally provide full set of operations for these first three categories. That is the arithmetic and logical, data transfer, and control. And by control operation, I mean branch, jump, procedure call, return, and trap. And of course, we will talk about these in detail in the later part of the course. And let me give a simplistic view of these three on this next slide. By arithmetic operation, we may mean add, subtract, multiply, or divide. For example, this is a 3 operand add instruction which says that add the contents of register R1 and R3 and place them in register R2. Similarly, this instruction says add the contents of register R1 and the memory location pointed to by this pointer foo in this register R2. Similarly, in case of logic operations, we can have AND, NOT, and OR. And this particular instruction says perform a bitwise operation of the contents of register R1 and R2 and place the result in register R1. Finally, flow control instruction change the flow of control. That is, instead of executing the next instruction, the program branches to the address specified in the branching instruction. And 4 types of control operations are conditional branches, unconditional branches, procedure calls, and procedure returns, as I have already mentioned in the previous slide. And of course, once again, we will talk about these in detail when we will be designing the assembly language for our hack computer. But for the time being, uh, this instruction go to 200 is basically a unconditional jump, which tells the processor to shift the control of flow to the instruction located at address 200. And this is a conditional branch which says if this condition is true, only in that case go to this instruction, otherwise just follow the sequence. Okay, so now is the time to talk about one of the most critical dimension of every ISA, and that is the memory addressing models and addressing modes. Well, by memory addressing model, we mean the view of the memory layout available to the assembly programmer. And by addressing mode, we mean the different ways in which the operands of an instruction can be specified. Let us talk about them one by one. First of all, the most basic memory layout model is called the linear memory model or the flat memory model. We will be using this model for our hack computer as well. This model refers to a memory addressing technique in which memory is organized in a single, sequential, and contiguous address space. To give you an example from history, in 1974, Intel introduced its 8-bit Intel 8080 CPU with an address bus of 16 bits. The designers of Intel 8080 processor used the linear memory model to access memory, and the processor could access a total of 64K locations using the 16 lines of the address bus. And the addressing was quite simple. You just put a 16-bit address on the address bus and you get back the 8-bit value that was stored at that particular address. And it is important to note that there is no necessary relation between the number of address lines in a memory system and the size of the data stored at each location. So the 8080 stored 8 bits at each location, but it could have stored 16, 32, or even 64 bits at each location, and still have 16-bit memory address lines. So this is an important concept that I want to tell you. Well, although we will be using the flat memory model in the design of our hack computer, but let me give you an overview of another famous memory model called the segmented memory model. Well, dear students, a segmented memory model divides the system memory into groups of independent segments referenced by pointers located in special CPU registers called segment registers. As an example, in 1978, Intel introduced its 16-bit 8086 CPU with an address bus of 20 bits, that is, with a maximum memory support of 1 MB. Intel also wanted to port all the assembly programs running on its previous 8080 to run on 8086 as well. And we have seen in the previous slide that 8080 could address 8086 could address 16 times as much memory as 8080. And to get the best of both worlds, they introduced the segmented memory model. To make this porting possible, Intel set up the 8086 so that a program could take 64 KB segments within 1 megabyte of memory and run entirely inside it. And this was done by the use of segment registers, which are basically memory pointers located in CPU registers, indicating where within the 8086 megabyte of memory a complete program ported from 8080 would begin. Another logical argument in favor of a segmented memory model was that every program has three logical parts: the code, the data, and the program stack. These three logical parts of a program should appear as three distinct units in memory. But making this division is not possible in the linear memory model. and the segmented memory model does allow this distinction as well. Well, dear students, in the next part of the course, when we will start with the assembly of x86-64, I will discuss other memory models that Intel introduced with the invent of its processors like 8286, 8386, 8486, Pentium and so on. And at that time, of course, I will discuss in detail about the working of this segmented memory model. And for the time being, we move on to the addressing modes. Well, in assembly language programming, the term addressing modes refer to the way in which the operand of an instruction is specified. Different architectures support different addressing modes. When an instruction requires two operands, the first operand is generally the destination, which contains the data in a register or memory location, and the second operand is the source. And generally the source data remains unaltered after the operation. And this is what we have seen on the previous slide as well. Well, today I will talk about 3 or 4 basic modes of addressing, and these are the register addressing mode, immediate addressing mode, direct addressing mode, and register indirect addressing mode. Let's see an example of these addressing modes. Let's suppose this is a snapshot of the memory, different addresses and the contents located inside the memory at those addresses. And let us suppose that there are different registers, namely R1, R2, R3, R4 and R5, having different contents. Well, in register addressing mode, both the operands are placed inside general purpose registers, and the register codes, of course, are specified inside the instruction. So this is the register addressing mode. Both the operands are inside the registers. In immediate addressing mode, one operand is in register and the other is part of the instruction as a constant. So this add operation will add the contents of the register R3 and this constant 54 and will place the result in R3. The limitation of immediate addressing mode is that the range of the constant or the operand that is specified inside the instruction is restricted by the available bits in the instruction. In direct or absolute addressing mode, one operand is in the register and the other is inside the memory, whose effective address is part of the instruction. For example, this instruction will add the contents of register R4 and the memory contents located at address 750, which is 50, and will place the result in R4. So if R4 contains 60 and this memory location contains 50, so finally after this instruction gets executed, this register R4 will contain 110. The fourth addressing mode I'm going to touch upon is the register indirect, in which one operand is again inside the register and the other is in the memory, whose address is placed in a register which is specified in the instruction. So this add instruction over here will add the contents of register R2, which is 50 over here, and the memory location whose address is there in the register R5. So R5 contains 500 and the memory address at 500 contains 800. So this 800 is added to 50. So the contents of this R2 register after this instruction get executed is 850. Dear students, please do a working of these examples using a paper and pencil and considering different values in these registers and at these memory locations. Okay, so other than addressing the memory, we also need to address different I/O devices. For example, a processor may also need to read or write the keyboard, a mouse, a monitor, or a printer. And the linking of the microprocessor with these I/O devices is called I/O interfacing. An I/O interface acts as a communication channel between the processor and the externally interfaced device. And this interfacing can be done in two ways. The first is the memory mapped I/O and the second is the isolated I/O. In memory mapped I/O, both memory and I/O devices have same address space. Excuse me. So addressing capability of memory become less because some part of the memory is occupied by the I/O. And in memory mapped I/O, there are same read-write instruction for the memory and the I/O devices. So CPU are cheaper, faster, and easier to build. The I/O devices, in case of isolated I/O, are given separate addressing region, separate from the memory, of course. And these separate address spaces are known as ports. Dear students, in isolated I/O, there are different read-write instructions, while in memory mapped I/O, of course, there are same instructions that are used to read the I/O device or the memory. The example of isolated I/O are in x86-64. Well, dear students, in upcoming lecture slides, upcoming lectures, we will be using this memory mapped I/O interfacing. When we will interface a keyboard as an input device and a screen as an output device with our hack computer. Okay, so now the last dimension of ISA is how the machine instruction, that is 16 or 32-bit machine instruction, is encoded so as to contain different information that we have discussed so far. So the first $100 question is, what is the size of an instruction? Is it 16-bit or 32-bit or 64-bit? And is it of fixed length or is it of variable length? For example, the MIPS architecture used fixed length instruction, while the Intel architecture used variable length instruction. x86-64 processor has the instruction size varying from 1 byte to 15 bytes. Another $100 question is, how many bits we are reserving for the opcode. For example, if the total instruction size is 16 bits, how many instruction bits, how many bits out of these 16 bits we are going to keep for encoding of the different operations. Another $100 question is, how to encode the operands. That is, if they are registers, if they are constants, or if they are inside the memory having the address inside the instructions. And another question is how we are going to encode the different addressing modes that this particular ISA is going to support. And finally, how come from the instruction the control unit can manage the flow of the control mechanism. My dear students, please do not worry. I am just giving you an overview of the general concept of ISA. You will inshallah get the answer to all these questions in the upcoming 3 or 4 lectures in which we will design the ISA for hack computer. This slide gives you a brief summary of some real world instruction set architectures. For example, x86 architecture at the top tells you that the class of the ISA is register memory. The maximum operand support is 2. The data size support varies from 8-bit to 64 bits depending on the different architectures. The count of the registers range from 4 to 24. The address bus is of 16-bit, 32-bit and 64-bit in different architectures of x86. For example, in x86-64, the address size is of 64-bit, and in 8086 it is of 16 bits. And similarly, you can see the stats for the other architectures as well. Okay, dear students, that is for today's session. My dear students, please have a very clear understanding of these 5 dimensions of an ISA. I have just give you theoretical information of these dimensions, and of course in the upcoming sessions we will see them in detail when we will design the different dimensions of this ISA for our hack computer. Uh, I think today's session was informative for you all, and if you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.